you doing? Good? How's the homework going? Easier? It's easier? Easier because you already did something like it? Good. How about the TensorFlow Keras one? Is that fine?
Oh, that one's easier.
Yeah. If you use TensorFlow or Keras, it's like way easy. If you haven't, it'll take a little bit of time to get used to. Yeah, that's the way you should feel when it's all. When you start using TensorFlow or Keras, it's so much easier.
I do have a question though. On the first notebook, it says get 100% over video. What could we get like 98%? Is that like good enough? Or should we?
That's a good question. I'd have to go look at like when I did it. I'm pretty sure I got like basically 100% of the video. I mean, 90% is pretty little bit.
That's what I think is what I wasn't. I wasn't sure.
Yeah, I mean, I would check that. Like, you really should be able to get pretty much 100%. Because it's just such a tiny. But I'll check that. Like for some reason, I'm pretty sure I got like 99.9. And like 2%, which isn't like a lot, but it could indicate that something is not taken wrong. Yeah. Okay. Let's get started. So, just administrative stuff. So the homework 2 is due by the end of the day on Friday. And it sounds like at least people who are here, it's like okay. At least a little bit easier than last time. That's good. I don't have homework 3 ready yet. I probably won't have it ready this week, but fall break is next week, right? So like, I'm totally gonna get it. That's what I'm gonna do on my break. But yeah, I'll have that. I'll try to get that posted as soon as possible. Like this last one, it might take a little bit of time, but I'll get that going. What else? Are we thinking about projects? You guys starting to get the teams and stuff? Because we'll have next week. We'll have the fall break, and then it's not the first week we're back. I think the second week we're back. Is that right? I should actually check. But I think that's when the project proposals are due. So that's coming up pretty quick. Hopefully you're thinking about that and identifying people to work with. Okay. Any questions before we get started? No? All right. There we go. Okay, so this is our last week of thinking solely about convolutional networks. In just a short amount of time, a couple of weeks, we really moved through a lot of different things. We've looked at lots of the popular architectures and how they differ from each other and what they're trying to accomplish or what each one was trying to accomplish at the time. We've looked at some ways to visualize what's going on, think about what's going on. And today, this week, the idea is to go a little bit further and talk about object detection and segmentation within images. So up to this point, we've only talked about classification of what's in the image. So, if there's like a dog in this image, we want there to be a classifier that says dog. But now what we want to do is we want to be able, within that image, detect where the dog is, and even be able to segment out like which of the pixels represent that dog, or that dog. So that's what we're going to be starting with today. So I feel like this is like really low resolution. Like it's even low resolution on my weird screen here to understand. Better here, but not sure. Does anybody else have a class in this classroom? No? Maybe it's just a projector, I don't know. Okay, so like I was just saying, so far, this is what we've done. It's like we train these things to classify, there might be 1,000 classes, and we want it to accurately pick out the thing that's in that picture. But oftentimes there's like more than one thing in the picture, and we might care more about like where that thing is. So there's a number of different tasks associated with this that we're going to start looking at. So then they have names. So there's this task of what's called semantic segmentation. So what you'd like to be able to do is take this cute cat picture and be able to say which pixels are associated with, say, the cat, with grass, with trees, with the sky. That seems like a pretty difficult task, and it is, but these are solved, maybe not surprisingly, again, with convolutional networks. Here is, for a single object, we want to do, say, classification. So again, noticing that there's a cat in there. But we'd also like to say, like, where is this cat? And often, if we're not doing segmentation and we're just doing localization, we'll often say that this thing has been localized if we can draw a rectangular box around that object, often called a bounding box. And this is, we'd say, okay, well, we've localized that. And object detection, this is object detection, it's localization detection. Object detection is when you can, for different instances of these categories within your image, you can sort of draw a bounding box and say, within that bounding box, there's a dog, and there's a dog, and there's a cat. That task is known as object detection. And instance segmentation is very similar to that, but again, when we say segmentation, we really are saying, we want to say like, which pixels exactly are associated with each of these instances. So, these pixels that are now in red are associated with this instance of dog, this in green, this instance of dog, and that blue, and cat. And this actually is a pretty difficult task, but has been more or less solved using convolutional networks. This is just to point out that there's a difference between 2D object detection, which is what we typically think about when we're talking about detection in images, but especially when it comes to like self-driving cars, there is this notion of being able to do 3D object detection. So obviously the image is two-dimensional, just physically, but often this is, especially like on a car, so this is a representation of something in the three-dimensional world, and we'd like to be able to bound the spatial extent of the objects that we see there. So we'll eventually get to like, some of the techniques of how that's done as well. Okay, so let's start into this. So semantic segmentation. So again, like the task here is, when we just talk about straight semantic segmentation, we just want to be able to, like each pixel, we want to be able to say, like what sort of an object is that associated with. So, in this picture of this cat that we keep seeing, we want to be able to identify all of the pixels in that are associated with the cat. And then there happens to be also grass and trees and sky. In this other picture, there's 2 cows, but like in this task, we're not trying to segment the two different instances of cow. We just want to be able to say like all these pixels are associated with cow. So how do we do this? What's an idea of how we might do this? Using ideas from like convolutional networks. That's the first thing you might think about doing if you wanted to solve this problem. What kind of training data would you need?
So objects which are clearly distinguishable from the background.
Okay, yes. When you say to clearly distinguish, what do you mean?
Visibly, like pixel data basically.
Yeah, so like you could go into an image and you could like take each pixel and say this is the cat. Yeah, okay. Yeah.
Just use like the series maps that we were talking about earlier.
Yeah.
Or just find where
Yeah, those
pixel attributes we have.
Yeah, so if we already have a label for like what's in the image, we saw how those saliency maps would allow us to segment out the the particular object in that image that those pixels that are associated with predicting that. Yeah. Right. So like basically like we need data here that where all of the pixels are labeled to be able to really do this well. That's hard to come by, but some of it exists. But what you might, if you didn't have that, what you might think about doing is actually say like, we have our convolutional networks that are trained to classify. Let's just like slide some sort of small window around this image, and for each of those small patches of the image, let's just classify that. Right? So we might hope that like we could pull this thing out and say like, oh, like that, that's a cow, and this is also mostly a cow, and this is mostly grass. And actually, this actually maybe it seems surprising, but it actually works pretty well. Even though we had trained on these larger images, because the training techniques do a lot of cropping and stuff. It's not necessarily that we train on the whole image to begin with, but smaller crops or patches of the image, and this actually works quite well to be able to do this kind of thing. And you can just run this window over the whole thing and say, okay, I've now classified, what this is indicating here is you'd say, if I classify this patch as cow, then I would like take the center pixel or like the center few pixels and say like all those are cow, and then same thing here, like these are all cow, these are all grass, and then we'd say, okay. Now we've labeled all of the images and, all the pixels in the image, and yeah, so we have our semantic segmentation. And that's fine. It actually works pretty well, but there's kind of a problem with it. What do you think it is?
Computational cost?
Yeah, so it's computational cost, right? It's just like, it's really, really, really inefficient to, on these images, if you wanted to do this, to run this thing, like, each pass through this window, like I said, on this image, I'm not sure how many there would be, but there would be thousands and thousands and thousands of these inferences you'd have to run just to do the semantic segmentation on one image. And like it's pointed out here in this note, you're not reusing shared features between the overlapping patches when you do this as well, right? Like, if I just shift this a little bit to the left or the right or up or down, I mostly have the same pixels, and I should be sharing. Like if I classified, one shift to the left as cow, I should be sharing it somehow. So, how do we solve this?
You can use other algorithms.
Use other algorithms, but then that would defeat the purpose of this class. And those algorithms are part of the past. We're moving to the future. Yeah, you were right. We're just going to do fully convolutional networks. What we'd like to do is be able to train something that actually starts with an image, a full image, so like whatever the height and width might be by 3 channels, color channels. And we'd like to be able to just run convolutions all the way through until, if we had the labeled data to say like, this pixel is cow and grass and whatever, we'd like to be able to make the prediction saying like, we would make one prediction per pixel, completely match with this and say, this is the class of this pixel, this is the class of that pixel, and so forth. Yeah, like this is the kind of thing we would like to do. We'd like to rely on convolutional networks to be able to do this. How is this different from what we've been doing?
The number of predicted labels are huge.
Yeah, exactly. So, if this is like 256 by 256, then that's a huge number of, so like, when we're just doing the classification, we're just making one prediction for the whole image. Now we're making one prediction for each of the pixels. So now we're making a huge number of predictions for each one. So like, that's really different. That's what we're asking it to do, but that's really different. How else are these networks like, I mean, this is just kind of stylized up here, but how else would is this network different from like the networks we were using to do classification?
There's not like a fully connected layer, and it looks like it's just ends up like an armrest.
Yeah, right. So it's not like it's fully connected layers at the end. But like we really can't have fully connected layers at the end because that fully connected layer is in anticipation of making one prediction, right? But we need to basically have like a whole bunch of fully connected layers here to make each prediction at each pixel. Yeah, I mean, like the point is like for this to work. So when we did classification, most of these networks, they would, through doing convolutions with strides or max pooling with strides larger than one, you were like reducing the spatial dimension as you move along through the network. But something like this, like just stylized the way I've drawn it here, is like we are not reducing the spatial dimension at all. And while that's like not that big of a deal, like conceptually, like computationally, this is huge. Like we are having to do again a huge number of operations to be able to maintain the spatial dimension, and especially if we have like a very deep network. So yeah, the problem is these convolutions are really, really, really expensive to do. And we kept it this way because, like, we could go smaller, but the problem is that we want to be able to make a prediction for each pixel. So, like, if we reduce the spatial extent, at some point we have to kind of like we have to get like bigger again, but we don't know how to do that. At least not yet. So the way this is done is this was a slide making that point. So the way this is done is yeah, we want to be able to do we want to be able to do this spatial downsampling, but eventually we want to be able to like upsample. So we know how to do the downsampling. We know how to do that. This is done through things like pooling and strided convolutions. But the upsample we don't quite know what to do yet. So throw out some ideas. How do we upsample convolutionally? So we'll be brave and try an idea. We know how to do this. This is easy. Like we talked about the strides. We basically just like we're just sliding that filter over the image, but instead of moving like one pixel to the right or left or up or down, we might move 2 or 3 pixels. Yeah.
Can you do like a reverse average pool where you like, you just use like 1 pixel and expand it out? That's a bad idea probably, but.
No, actually, we actually do this. We actually do bad ideas. We actually do really bad ideas. Yeah. So here you go. Yeah. So there's this notion of unpooling. Now this isn't like this is used. This is not the most common thing to do, but it's definitely used. So I think this is what you kind of were thinking about in your head. It was like, okay, well, if we need to, if we are at 2 by 2, we want to go expand by a factor of 2, like unstride by a factor of 2. Then there are some things we could do. Like we could just say, okay, everything, this upper left-hand quadrant is going to take the same value as this, and so forth. You can see the patterns there. That's upsampling. Like it's basically that you're going to have exactly the same image as you had before. It's just like your resolution is going to look worse to your eye because even though you have like more pixels you're looking at, you have 4 pixels describing the same information as 1 pixel. So like it's actually will appear to be at a lower resolution. There are other things you could do that might even seem even worse, but you could do this thing over here, which is like zeros everywhere except where you pick one of the entries in that quadrant to have the original value. Was there a question?
So could we do something like take each number and maybe generate 4 random numbers which add up to that number?
Sure. Yeah, we can do that. I've never seen that, but we could do something like that. But I mean, this is like what people are, this is what people started to kind of experiment with. Yeah, so this is like some notion of like unpooling, right? Where before like pooling is, go from something of larger spatial dimensions to smaller spatial dimensions by picking some representative out of there or like some average out of there. Now we're sort of trying to go the other direction. The trouble is, it's easier to go from more information to less information. Here, what you're trying to do is go from less information to more information. And that's the thing that's like, yeah, should be hard to do. Yeah, like, here's another idea amongst all the bad ideas we're coming up with. Max unpooling. So yeah, max pooling, you know how this works. Here's an example of how that works. But if you want to max unpool, then if what you have are corresponding pairs here, so like a lot of these networks where they downsample and then upsample, there is often like a paired layer. So like there's like some sort of symmetry in the way of going like when we reduce the spatial extent and then when we increase it again. I'm not really sure why that is, other than there's some expectation that we're not creating like weird bottlenecks of information loss as a result of that. So if you have that and you know where, like in the matched layer when you were downsampling, if you know where the max value was, then when you do the unpooling part, it's like that, what was called in quotes, bit of nails, but instead of just putting it in like some fixed position in all the quadrants, you use where the max position was. Is that a good idea? I don't know. It's just stuff that people try. What is, like pooling, like we looked at before, what is a characteristic of this that seems kind of undesirable? Yeah, so there's information loss. And in particular, we are not using the data to like help us to unpool, to upsample. Right? There's no learnable parameters in this. Like, in max pooling, one of the reasons we like it is because it's a really inexpensive, or any kind of pooling, it's a really inexpensive way of reducing spatial extent. But there's also another way to do it, which is a learnable way, which is to do your convolutional filters, but then use a stride greater than 1. So there is basically, so for upsampling, there's basically the reverse notion of this, and that is these are what are called transpose convolutions. So this introduces learnable parameters to allow us to learn to go from lower spatial extent to smaller spatial extent to a higher spatial extent, to go from to upsample. So if you think about, so to motivate this, the way this works is like, okay, so for convolutional filters, in this example, say we have a 3x3 filter, stride 1, pad 1, so we're allowed to be centered up here in these corners. These are just zeros. We know how to get to the feature map, to the output. And that is just to do that dot product of all the values in the filter map and then the input, and then that becomes our output. And we slide this along. If it's stride 1, if it's stride 2, then we just skip a pixel and move over. And yeah, this is like pretty. Hopefully, it should seem really pretty familiar at this point. To do the transpose convolution, what we want to do is go in the opposite direction. So we want to be able to say start from this 2x2, but with a stride 2 go to a 4x4. We want to be able to undo it. So how do we undo it? Well, there's basic. I guess we'll get to this in a second in the slides. But we want to be able to produce a set of numbers that will appear here in this filter and in this filter. And the stride 2 again says something about like where these two filters are in relationship to each other. And whatever these numbers whatever these numbers are that we produce, if there's any overlap, we want to do simple things like add them up. Whatever numbers are there, if we overlap, we want to add those things up. And that's sort of like, it's sort of analogous to what we're doing when we're doing stride 2 convolutions, like regular convolutions. Yeah, like this is just saying that like there's different names for this kind of thing. It's best to call it transpose convolution. We might see like all these really weird names, but it's mostly called transpose convolution right now. And there's a reason for the transpose. We'll get to that in a second. But like here is, there's actually this slide here. This is something about like in any overlap we want to add. But like what I think makes this easiest to understand and why it's called transpose convolution is the following. So you can think of like the operation of convolution as like a matrix multiplication. So here's just kind of like a stylized example. You know, we can think about the let's see, what's the filter here and what's the, so I guess like this is like our input right here, and these are the filters as they sort of move along, in this case like in a stride 1, in the padding of 1, the example is like where all the zeros are here. So you can write down the convolution as a matrix product, and this is for stride 1. And you can do this also for the transpose. You literally take your filter and you transpose it. You're going to have a bit of a you're going to have a different spatial extents here, just given the way that the matrix dimensions are. But if you think about like what's happening here, and you just sort of transpose that idea, then you get something similar over here to what was here. They look like each other, just in form, and yeah, like it probably seems weird to like just look at it like this. Yeah, it does look really weird to me to look at it like this. Actually, these should be Z's right here. This is what looks funny. These right here should be Z, 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 to match what's going on over there. But anyways, so notice what's happening here. When I do this convolution right here, I go from a vector of length 6 to a vector of length 4. That just accounts for the padding. When I do this transpose over here, I go from a vector of length 4 to a vector of length 6. That's to account for, say, like the ups sampling. Where this is maybe more interesting is when you have the stride 2, where we actually do the true upsampling. In a stride 2, again, this is wrong. But in a stride 2 example, where we're not, you see how this is shifted to the right here in these entries. You know, we've gone from really dimension 4 to dimension 2. When we go the other direction, we're going to go from dimension 2 up to dimension, it really should be 6 here, but because of the padding of waves to not get, well, it's 6, but there's a 0 here. You get this, you get this expansion of the dimension. So so from what you know from linear algebra, what's problematic about, say, operations like this when you go from lower dimensions to higher dimensions?
Have like no solutions or any solutions?
Yeah, I'm not sure you're saying that, but that's right. It's like, yeah, so like when you go from low dimensions to high dimensions, you can basically do that in like many ways, right? And this is corresponding to the fact that there's like we're going from less information to more information. There's a lot of ways to expand that way, and so this technique sort of like suffers from this idea. There's like a lot of ways to do this, and yet when we train these networks end to end, where we're doing this transpose convolution, and sort of gaining information, we are still supervising what is happening in, what parameters we're learning in that transpose convolution, we're still learning those as part of the full optimization. So it is picking out like a solution out of the many there, the infinite number that there are to satisfy those constraints. So it is somewhat, determined, but it is really not a determined problem. And yeah, like that, I'm just pointing it out because it's like, it should cause like some pause that's what's happening here. But it's okay because like with most things in neural networks, it just works. It works great. And it turns out that when you do this sort of downsampling and upsampling, you really restrict the number of parameters that are in the network, so it makes it feasible to actually train. And you can do this kind of thing really well. Where you are making predictions, one prediction for each of the pixels. Questions about that?
For your training set, how do you?
You get every pixel label. You just have like graduate students and postdocs. Who's used Amazon's Mechanical Turk before? Yeah, this is a tool that you use. You pay people not very much to label stuff for you. Basically like someone sits down with Mechanical Turk on something like this and like draws like the boundaries around these things. It's a horrible thing. So yeah, so you can do this kind of this semantic segmentation, but it's really expensive to get the data, and therefore you don't really see it all that often. And there's ways to like bootstrap yourself from like, so like say like you have like very similar types of images, like there's correlated images, like I don't know. I mean, if you have a video, then there's a correlation in time. If you have just like one thing labeled or a couple of those things labeled, you can usually pretty easily, not through convolutional networks, but other techniques, just like label the rest of the images in between, say time points. But yeah, it's pretty. Yeah, the amount of work going into that is really, the amount of cost going into that is really bad.